Hello everybody, today I'll show you how you can continue with the generation of the PCG building graph. The last time we created the graph for generating a single floor, and now we can extend this graph to generate all the floors with a different type of elements for each floor, and even different type of elements for a single floor, like we have here. On the first floor, for example, I can have different type of setup for the doors and the garage doors. And for each of the other floors, I can choose the placement of the different type of windows. So let's continue where we left off the last time. I'll delete this building for now, and we'll continue with the generation from the point that we left off in the previous tutorial. If you have not watched it and you don't have this script, please check the previous video, the PCG building tutorial part 1. So let's open the main graph, and you see that the main graph is only consisting of these variables that we get from the blueprint and this subgraph that we are using to create the single floor. So this will cause a problem where if we want to place different type of elements for each floor, this single floor graph currently is placing every time the same elements. So if I open here the mesh entries for this static mesh spawner, we will always place this element for the corners. And this element, let me open it. This element has this base concrete part, which is only suitable for our first floor. So we need a way to spawn a different element for each of our next floors. So let's go into the single floor subgraph and change it that it will not spawn the same element, but it will just export the points that we are generating, and we can have a logic inside our main graph to decide what should we place on this point. Go into the subgraph, and for now let me show you that one quick fix from the last time. We have moved the points over the floor surface because I wanted to show you where the facing direction for each point, and they were under the floor, so I moved them up a bit just to be able to show. But now that we have the meshes placed and we can see the direction from the mesh, we don't need that. So let's go into the subgraph, and let's go here where we use the ceiling height divided by 2, and we connect that to all the transform points nodes. Let's delete this whole part here, so the ceiling height, the division by 2, and now there is no more Z offset, and it's placed directly on the floor like we want it. So now let's continue with the step that I talked about earlier, how to be able to spawn different type of elements for each different floor. So instead of spawning the points, we will output all of the points from our subgraph, and we will use custom property to tell us what type of point this is. So here, where we are placing the corner elements, I can mark this static mesh spawner. I can hit the E key, and this will disable and enable it to see what it's doing. So this is spawning the corner graph. So let's disconnect this, and instead of spawning the corner graph, let's add an attribute, and let's have this attribute be called, let's say, type, and it will be of a type string, and the value will be corner. Now if I mark any node and hit the A key, I will get the attributes for each point, but I need to select which graph I'm referencing. So go here at the bottom of the panel, choose this subgraph node. And now if I go to the end, I'll see that this is generating a point with the type of corner. So I'll do the same for my pivars. So instead of spawning the pivars here, let's disconnect it by out-clicking the connection. I'll add the attribute, just copy this node, connect it here, and I'll add the attribute, but now the value will be a pivar. I'll do the same for the walls, so disconnect, connect it here, and the value will be wall. So now I have all these three types of points, and we are no longer placing our elements inside the subgraph. So I'll cut these nodes and I'll paste them into the main graph. Let's paste them here. Okay, now let's go into the subgraph and we need to output these points into our main graph. Find this output node, move it here at the end, and now let's connect everything to this output node. Open the pins element, let's delete everything from the pins and just create a single pin. This pin will be of a type point, will allow multiple elements and multiple connections to this pin, and we'll call this pin 4 points or single 4 points. And let's connect all the points that we are creating from the three type of elements into our output pin. Let's save this. Let's go back to the main graph, and if I connect these points to any element, you see that for each point we are spawning the type of element into this static mesh spawner. We want to split them into all these three nodes, but we want only the corresponding points for each one to be used to place the type of element that we are defining for the different type of point. So let's do a point filter. Let this point filter be checking for equality, so the operator will be equal sign. The target attribute will be the type that we created. We'll use a constant threshold. The type will be string, and we'll check for a corner. So inside this filter, I will have all the corner points generated by this subgraph. So inside filter, I'll connect to this static mesh spawner with the corner element. Here I have the corner element set up to be placed, and the filter is selecting only the corner points. So points that have the target attribute set to corner. Now I can now filter all the points again the same way, but it's probably easier to filter only the points that are left that are not corner. So I'll do another filter here, an attribute filter. Actually, let's copy the last one. So we have preset the target attribute to be type and this operator to be equal sign. And now we'll check for a pivar. Inside the filter will be all the pivar points, and outside the filter will be all the wall points. Let's do one additional filter. We can just connect the outside filter now, because the only points that we have left are our wall points. But for now, let's just do another filter to be sure that if we add some additional points into our generation, we are not spawning walls for them as well. We will be having another filter for them if we need it. So let's connect this filter. Let's change this to a wall. So now we are filtering all the points from our subgraph and spawning a different mesh for each of them. Let's create a subgraph from this, so we have a better way of doing this multiple times for each 4. So let's collapse this into a subgraph. Let's go into the same folder that we had before, and let's call this a PCG subgraph split single 4 points. So now we have one input, which are all of the points that we are generating, and then 3 different outputs. Let's go into our subgraph, the newly created subgraph. Let's arrange the nodes a little bit better than the automatic arrangement, like we had it before. Okay, so now all the points are coming in, then we are filtering them 3 times, and we are outputting the points here. This out, it's not connected to anything, so let's delete it. This inside filter, the first one, will be our corners. This second pin is our pillars, and this last pin is our walls. Okay, so now if I go back to the main graph, let's save it. I have first this subgraph to generate all the points, then this subgraph to split them, and we are placing different element for each type of point. So we have the result from before, but we can now do it differently for each floor. So let's continue with generating the floors based on the height property. Here I have the height property from my blueprint. Currently, if I select the blueprint in the level and change this height field, it doesn't do anything. It's not connected to any type of logic inside my PCG graph. So let's use this height property to spawn different number of points based on this property along the z-axis. So what we did into the single floor, let me remind you here, is we created a point grid. We calculated the grid extents and the cell size based on the sizes of the elements for our meshes and the setup that we want for the building height, width and length. So now we need to do the same thing, but for the height. The height of the building will be this height field multiplied, drag out of this height variable, choose the multiply field. Now this will be multiplied by the height of each floor, which is this ceiling height property. So we will multiply the height of our building by the ceiling height, and we'll generate a point grid. So right click and do a point grid, create point grid. So what we need for this point grid is the grid extents and the cell size. So the cell size, we want a single point for each floor. So because the cell size needs to be one wall thick, or actually we even don't need it to be a specific size. Let's say that the cell will be, let's create a vector, make vector, and the type of the vector will be with 3 values. So the important thing here is that the z size of the cell is equal to the ceiling height variable, so we can control the height of each floor. And this x and y, let's say we'll make an attribute, create attribute. This attribute will set a value of 100. and connect it to the X and Y. So it doesn't really matter what's the size of our point for the generation of each floor. The important thing is that it's based at the ceiling height that we set up. So this will be our cell size, and our grid extends will extend half of the size of our horizontal element cell size into each direction. So let's get this attribute and divide it by 2. So divide. Let's create another attribute and have a value of 2. So now let's divide this. And we'll have another vector. Let's copy this make vector. And we'll have the X and Y, this half of this size. And the Z value will be the multiplication of our height and our ceiling height. So for each floor, we'll have to generate a point. Let's connect this to the Z value. And now this will be connected to our grid extends. Let's debug this create point grid. Now, because it's a little hard to see when all the points are the same color, I'll stop debugging this and I'll create another node after this with an attribute noise. So this attribute noise will choose the noise to be the density, the output again to be the density, because the density is the one that's default controlling the color into the debug. Mark this and hit the D key. So now it's easier to see the different elements. Each element has a random value from 0 to 1. So the color is different. Now that we have 4 points into the height setup of our blueprint, we are generating 4 elements for each floor 1 point. If I change this to 2, 3, 4, 5, you see it's dynamically generating the number of floors that we set up here. The single problem now is that it's generating also points below the surface of our building. So to fix this, let's go into our blueprint. So open the blueprint for our building, and let's make sure that into our blueprint we can create a variable here called position. Let's make this variable a vector type. Let's make it public in order to be able to access it into our PCG graph. Compile and save this blueprint, and go into the construction script of the blueprint, out drag this position variable, and when we create the blueprint, let's set the value of this position variable to the actor location. So get actor location and set the value of our position variable to the location of our blueprint. Compile this and save it. And if we go back into our PCG script, let's do a point filter, and let's make sure that here into the point filter we choose the greater or equal operator. Let's choose the position value and type a dot and then Z. So we will compare the position Z value of our points with the, let's copy this get actor property node. Let's put here the property name of position, the new property that we created. Let's break this vector and let's use the Z value here. So into our attribute filter, make sure that we are comparing the position Z with the not with the density like it's set here. Let's delete this. And if we leave this threshold attribute name to none, and when we are getting this actor property, we are outputting it into attribute name none. So it will work that way. Let's go exit position and make sure that here into the threshold attribute you're using the same value. So now we are creating points up and down the point of our blueprint. And let's do this same trick with connecting an attribute noise for preview after this element. So if I preview this node now, it's properly showing you that it's only selecting the points that are with the position z bigger than the z position that we are outputting here. If I create another attribute noise and connect to this outside filter and debug this bottom one, these are the points below, the ones that are into this attribute noise below in the outside filter. And if I debug only the top one, these are the points that we are getting inside the filter. Inside our filter, we are getting the points for each floor. Like now we have set up to have 2 floors, and inside the filter here, we are getting these 2 floors. Let's stop debugging. Let's delete this attribute noise. And now we have to spawn these points for each floor. So to get the points for each floor to be replicated from the generation of this single floor to all of these floors that we are creating here, let's use a copy node, copy points node. So inside this filter, we want to copy points. And the points that we want to copy are actually the ones that we are generating for each floor. And the target, let's disconnect this inside filter and connect it to the target. So instead of creating the points only for the first floor, when we create them, we will copy them the amount of times that we want to have the number of floors that we set up into our blueprint variable for the height. So when we create now the connection between these copy points and this subgraph that's splitting the points into the 3 types, and when we are placing elements with this static mesh spawner, we will now have the elements for each floor properly spawned. And what we can do now is go into the level. When we select the element and change the height variable, we will be properly having the amount of floors that we set up here. Okay. Now, let's go back to our PCG graph and let's have different type of meshes for the first floor and the next floors. So let's select this blueprint. Let's say we'll have 4 floors. Let's go back to our PCG graph. And what we want is to save the number of the floor inside the points that we are creating for each floor. So before copying these points, let's get the floor points that we are generating, a single floor point for each floor, and let's copy attribute. Let's copy the index attribute. Let's choose the index and let's copy it into our floor custom attribute. So we'll be creating a for custom attribute. Let's disconnect this and connect it to a target. So each of our points will have a for value inside, and it will be the same as the index of our single point for the for. So 0 for the first for, 1, 2, and 3 for each of the fors that we're currently having, the 4-for setup that we have now. So if we click the A key on this copy points node, you can see into the for variable we'll have different number of the for. Let's actually hit the A key here. After this copy points, again we have for values. So if we do a point filter here, point filter, and we say that we want the for value, so choose the equal operator, type here for, and we want to have a constant threshold, so it will be an integer. We want the for value to be equal to 0. So inside this filter, let's disconnect this, we have only the points for the first for. Outside this filter, let's copy this, and outside this filter we'll have the points for all other fors. So for the other fors, let's choose a different mesh to be spawned. So for the corner, we don't want this base level concrete trim for the upper floors. So let's go back into our building and let's choose the 4x4 pillar kit, and let's connect this corner here, this corner, and connect it here. Now I can see that the upper floor meshes, let's continue with all of them and then we'll fix that. Let's connect the pillar, and for the wall, let's go and choose, for example, this. Okay, now I am spawning a different mesh for the upper floors compared to the base floor. The problem is that the meshes for the upper floors are smaller. For our building, let's go to the base pillar kit. Let's check this one. Okay, this looks to be better size for our floors. So now, if I use this pillar kit, base pillar kit, without this concrete base, my upper floors have shorter height. So only the first floor is bigger height than the rest, so it makes more sense to have the setup of our building here into our blueprint to have the ceiling height of 300, which is the height of the upper floor. And when we are placing this first floor, after this for each other floor, so outside this filter, let's do a transform points. And let's do 100 points offset into our Z value. So if I connect now this, I have each floor into 300 units high placement of the points, and for after the first floor I'm translating everything 100 points up, because the first stack of points is having the height of 400 instead of 300. This is for this set of Quixel elements for the Neo-Baroque building type 2. For the different buildings it probably will have different heights, and you need to change these transform points for the first floor or for the other floors. So just make sure that you have this into the main graph and not into the subgraphs for creating the points. That way you can easily change this for each graph that you are creating for different type of building. And we can reuse the same subgraphs to generate the points for each type of building. It's not related to the size of the elements. We have everything set in the variable. So now you have for the spawning of the elements for the first floor, for all of the other floors. But what if you want to do for specific floor some other type of points? So for example, the fourth floor has some special elements inside. If you go to the fourth floor here, you have a couple of folders, so different type of columns, a type of trim over the elements, and different type of walls with the different window. So let's do a different mesh for the fourth floor. How we can do that? The same way that we did here. When we disconnect these other floors, after we are filtering just the first floor by comparing the floor index to 0, outside this filter we are leaving all the other floors. So let's compare the floor number, not to a constant threshold, but let's create attribute. This attribute will be of an integer type and a value of 1. And let's use this get actor property for the height of the building. Let's paste it here. So let's do a subtract math operation. So make sure that you're creating a math operation and you have this operation set to subtract. So subtract from the height a value of 1, because we are starting the indexes of our floors from 0. So the last floor, when we have a setup with 4 floors, we'll have an index of 3. So 4 minus 1 will be 3. So the threshold attribute here needs to match the output target for this subtract. So currently it is the source, and the source is the last element that we are modifying. Here, let's output the result of this subtract into the last floor attribute. And now let's use into our attribute filter the last floor here. So for the last floor, inside this filter, we'll have only the last 4 points, and outside the filter, all the other points. So let's connect the other points to the ones that we already have here. Let's copy this whole setup that's placing our elements. And let's connect it to the last 4. And let's change the meshes for the last 4. Let's select the first point. This will be our corner pillar. Actually, let's first spawn the walls. So let's go to fourth floor set of elements and let's connect this wall. You can see that the fourth floor is higher, so I'll need a different pillar. So let's go to the fourth floor pillars, connect this bigger pillar. For the corner element, I'll connect the corner pillar. And now, after we spawn each of these elements, we'll create a transform point after it, transform points node, and another static mesh spawner after the transform, which will spawn the special trim for the last floor. So go to the fourth floor trim kit and let's connect this to the element that we are spawning. And with this transform point, we'll control where to place this. So move it 400 units. 400 is too much, so 350. Yeah, 350 is fine. So copy these transform points with the 350 units in the Z and static mesh spawner 2 more times, connect to each of the other nodes and change the element. For the pillar, it will be this one, I believe. Connect this to the pillar. And for the wall, it will be this long one. So now, if I enable and disable each node, you can see what's doing. This is the corner element. These are the pillar elements. And these are the wall elements. Trim for the last floor. Let's continue with generating different type of static meshes for a single floor. For example, let's add a door to the first floor of the building. So let's go back to our main graph. So when we are filtering the points for our first floor, so 4 with a value of 0, we are placing for the walls every time the same element, this type of wall with the window. So instead of this, what you can do if you want a randomly placed object is go to the folder with the meshes for your building and add a couple of elements. Instead of just having one element here into the mesh entries, you can add multiple entries. For example, I'll add another one, and here into the descriptor I'll connect the door. Now you have a random placement of doors and windows, and you can control the amount for each one with this weight attribute. So currently the weight of both of them is set to 1. So I have the window and the door set to 1. If I want to have a lot more doors, I can set the weight to 5. Or if I want to have a lot more windows, I can set the weight of the window to 5 and the door to 1. So I'll have a lot more windows. But what if you want to have a specific pattern that you want, for example, each second element to be a door? You cannot do this with just adding the entries here. So let's remove the second entry for now, delete this, and now we have only the window, and we can add a logic here by adding to our blueprint another variable. So go to the blueprint, add a variable and call it door repetition, and the type will be an integer. So compile this and save it. Let's go back to our PCG graph. So now where we are placing our window for the first floor, let's move here to see better. When we are placing this window, we need another mesh spawner connected with this door element. So let's connect this door to the descriptor of the mesh entry for this mesh spawner. Let's disconnect this. Let's do a point filter. In this point filter, let's connect the inside to the door placement and the outside to the window placement. So for now, because we're not filtering anything, everything is outside the filter and it's placing this window. If we select the filter, and let's say we'll compare the index of our element to a constant threshold, the operator will be equal and the type will be an integer. So now, when the index is 0, we will be placing the door. So let's find the 0 element. Okay, here it is. The index is 0 and we are placing a door here. Let's select the filter again. When the index is 1, we'll be placing the door onto the element with an index 1, then 2, then 3. To do this and to have it repeating, so now if I want every second element to be this door, I need to use a mathematical operator, which is called modulo, which is if you divide 4 by 2, the result of the division is 2 and the remaining is 0. If you divide 5 by 2, the result of the division is again 2, but the remaining is 1. So if you don't have a exact division, so 5 is not exactly divisible by 4, you will have a remaining element, so one element away, and this is what the modulo result is returning. So if I right click and create a modulo operator, if I connect my walls to this modulo operator, and here let's create attribute. Let's say this attribute it's 2, so let it be an integer and let's set it to 2. Connect here to the modulo operator. Now let's expand this a bit. So if I click A to get the results from this debugging, and if I select the modulo operator and save the result in a custom variable, let's call it repeat index. Now, if I choose for the input to divide the index, so I'm dividing the index by 2. So the index here, I have 0, 1, 2. So when I divide 1 by 2, I cannot divide it exactly, so I have a remainder of 1. So here I have a remainder of 1. When I divide 2, I have an exact division, so there is no remainder. So let's change this to 3. And you will see that now I have either exact division of the index or remainder of 1 or 2. This modulo is exporting this result into this repeat index element. So if I connect this here, and if I use the target attribute of repeat index and use a constant threshold of, for example, 2. So now when I divide my index by 3, I have a remainder of 1 or 2. So each element that have a repeat index of 2 will spawn door instead of the window. Now I have a way of spawning the amount of doors I want by setting this attribute. So I'll delete this attribute now, and I'll get actor property. The property name is door repetitions. So connect the door repetition. We are getting the door repetition property. We are dividing it into this modulo. So currently the door repetition is set to 0, as you can see. That's why we don't have any results. Now I do need to calculate this threshold, not to use a constant threshold. So I'll get this property and I'll subtract 1, because when you divide by, for example, 4, the maximum remainder that you can get is 3. So I'll subtract 1. So create attribute. This attribute will be an integer. It will have a value of 1. So I'll subtract that and I'll connect this to the filter. So now this attribute filter needs to compare to this property. So let's say this will be a repeat index. So copy this subtract output target, we called it repeat index, and place it here into the threshold attribute, repeat index. And now it should work. So save this, go back to your scene, select and change this repetition value. So now if I have 0, I don't have any doors. If I have 1, I have a door on each element. If I have 2, I have door on each second element, and so on. We can do the same thing for the windows, but on the other floors. So let's copy this exact setup. Let's paste it here. Let's connect the walls here. Let's go to our second floor meshes. Let's copy our mesh spawner here. Let's connect this different type of window. And let's connect these two type of windows. So now, instead of using this door repetition, let's say window repetition value. Let's go to our blueprint, add window repetition value. Let's make it public. Compile this and save it. Save this. Now I have an error here, so let's get actor property, get the window repetition. I have an error again, failed to extract window repetition. So window repetition, let's copy the exact name, make sure that it's compiled and saved. Does not exist. So if I select the PCG graph, the error disappears. So it looks like a bug just in here in the system. So let's connect this to the modular operator and let's connect this to this subtract. So now, if I close this, I have these two different elements to set up the repetition of my different meshes. So if I put one for the window repetition, I get a window on every, I get this double window on every element of my walls. If I put two, they are repeating. And currently the problem is that the indexes for this all the floors that are not this first floor are going vertically and not horizontally. So to fix this, export a value into our single floor graph. Sorry, not this, but the single floor generation of the points. So when we are adding the attribute for the wall, before this we'll add another attribute. So add attribute, and this attribute will add a value. For example, the output name will be horizontal index, and the value will be the same modulo operator like before, so modulo, and we'll use this to calculate the horizontal index. What we need to delete now to get the remainder of is the size of our floor. So the size of our floor is the width and the height multiplied by 2, because we have two walls with the length of the width variable and two walls with the length of the height variable. So go back here into the beginning, get this width and length variables, copy them. Let's paste them here next to our modulo. So get the width and the length, add them together, then multiply, create an attribute, make it an integer, put a value of 2, so multiply by 2. So when we add this width and length and multiply by 2, we get the size of the floor that we have. So we need to output this into a special attribute, because we cannot output this into the index. So first, let's say that we'll use the index for the input source. Last will be fine. And we cannot output into the index. We need a new attribute. So copy this horizontal index. I'll not need this attribute actually, because this module can generate our horizontal index attribute. So connect it here. Now, if I click the A key and select this subgraph, you can see that we are creating a horizontal index with value similar to the index. This is for a single 4 currently, but for multiple 4s, it will create this value for each 4. So now if I go back to our main graph, let's select our main graph, and if I use, instead of the index for this module, I use this new horizontal index value. Let's save this. And now, instead of repeating vertically by this window repetition index like we had before, now we can repeat them horizontally, properly, like we wanted to do it. And if you want to have a vertical repetition, you can have another modulo operator. Let's say for the other window repetition, let's go into the PCG graph. I'll add a blocked window repetition. And you can add more generic names, because for different type of sets of meshes, it will not be a blocked window, it will be some other type of mesh. So this is just an example, but let's make this public. Let's copy this. And if I go to my PCG graph, now outside this filter, instead of just spawning the same thing again, I can do the same setup. Here the actor property will be this blocked window repetition value instead of the window repetition. Now connect this here. Inside the filter, I need to place the blocked window. So here, let's copy this, connect it to the outside, and for the first one, let's use the first 4. So let's connect this here to the descriptor. Now let's save this. Actually, let's go back. And here, as I said, I don't want to place them horizontally, because I want this blocked window to be more randomized. So if I put a value of 2, I'll have repetition like I have for the double window, and I want this to be just a more randomized look. So I'll go and change this attribute filter, sorry, this modulo operator, not to use the horizontal index, but the index. And now, if I put a bigger value here, for example, 5, 4, I have more random look of where these windows are placed. It looks like some people have their windows blocked and some not. So it has some sort of random repetition. So let's click 6, for example. So if I have somewhere this blocked window and somewhere not, it's not repeating like the setup for our double windows. So the double windows, let's put 2. So we have each second column to have double windows, but this blocked one, we are using the index and the bigger value. That way it's counting vertically, and whenever it meets the condition, it plays this blocked window. So this way we have more randomized look for our building. So for today, let's say that we need to stop because we are getting this tutorial longer than an hour almost. So next time I can show you how you can finish generating this building by adding the windows and the roofs. The roof is a little complicated to do, so brace yourself for the next tutorial. But if you have any questions for the setup currently, please write in the comments and I'll be happy to let you know what's the answer or what you can change. So see you next time, guys. Bye.